Hi, today we're going to be looking at the derivative of e to the x. Now the derivative of e to the x is very easy. The actual derivative is going to be e to the x times the natural log of e. Now we're going to take a look at why this is later on when we get to something called logarithmic differentiation. But if you're interested on my second video, I'll kind of show you proof of this. Now we can simplify this because we all know that the natural log of e is just 1. So therefore the derivative of e to the x is just e to the x. And again, like I said, if you're interested in another video, I'll kind of show you a quick proof of it. Now, with that being said, let's go and take a look at some examples of when we take the derivative. For example, let's say we have y equals e to the 5x, and I want to find the derivative. Well, dy dx, or the derivative, it's going to be itself. We're going to get this e to the 5x. But you'll notice we do have a chain rule here. We have an inside. We have this 5 right here. So we multiply by its derivative. It's a chain rule. So I multiply that by 5. So therefore we get 5e to the 5x. And there's our derivative. Number 2, let's take a look at another example here. What if we have something like y equals, let's say, the sine cubed of e to the 2x. Ooh, nasty one right here. Now, we've seen this before. With the cube here, we're going to rewrite it as sine of e to the 2x cubed. So when I take the derivative, we have a chain rule. So y prime becomes, we get 3 sine of e to the 2x squared times the derivative of my inside, cosine e to the 2x times the derivative of the inside, chain rule, major chain rule here, e to the 2x, and I'm still not done because now I got to multiply by the derivative of 2x, which is 2. And there's our very, 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 very long derivative. And you can clean this up by making the 6 sine squared of e to the 2x times cosine e to the 2x times e to the 2x. And there's your derivative. We can apply all sorts of different rules right here. We can even apply our natural log rules. Like let's say I have the natural log of e to the sine of x. And I want to take this function's derivative. Well, I could go straight forward and take the derivative like so. Get y prime equals 1 over its natural log. So it's 1 over e to the sine of x times the derivative of the inside, which is our e to the sine of x, times the derivative of our other inside, cosine of x. And those cancel, and we're left with the cosine of x. Or I can remember my natural log rules. And in other words, natural log and e, they cancel each other out. And so we get y equals just sine of x. And the derivative, yep, is just cosine of x. So your properties, your log properties, are helpful in a lot of these situations right here. So let's take a look at a few more examples here. Number 4, let's take a look at another kind of an easier one again, just to kind of go back to the basics of it. For example, like number 4, what if I gave y equals 3x e to the 2x? Well, this is our product rule. This is our product rule right here. So when I take the derivative, we take the first times the derivative of the second, e to the 2x times 2, don't forget your chain rule, plus the second, e to the 2x times the derivative of the first. And there's your answer. You can clean it up if you want to, 6x e to the 2x plus 3e to the 2x. And there's your answer right there. Number 5. Let's take a look at kind of another easy one right here again. What if we have y equals, let's say, x squared plus 1 over e to the x. Of course, this should be recognized as our quotient rule. And so when we take the derivative, it's low times the derivative of the top minus high times the derivative of the bottom all over the bottom squared. You can write this e to the x squared or just e to the 2x. And there's your answer. Don't need to simplify that. There it is. And there you go. So e to the x is a very easy derivative to take. We can even do slightly more complicated ones. Like let's say we have y equals e to the xy plus x squared minus y squared equal to 10. You should recognize this one. Whoops, sorry, not y equals. Let's get rid of that. Sorry about that. You should recognize this. We have x and y's. This is our implicit differentiation. So when we take the derivative, anytime you take the derivative of an exponential, you're going to get that exponential back. So we get e to the xy, but if you notice we have an xy here, that's our product rule. So we have a product right here. So when we take its derivative, it's going to be times the first times the derivative of the second plus the second times the derivative of the first. Then go here, plus 2x minus 2y dy dx equals 0. Distribute before we do anything else. We're going to get x e to the xy dy dx plus y e to the xy plus 2x minus 2y dy dx. Now we've done these, equals 0 still. So we've done these before. Don't forget anything with the dy dx stays, everything else has got to go. So I'm going to rewrite this as dy dx, and I'm going to factor out the dy dx here, ex e to the xy minus 2y, and at this point you're like, man, where did all those numbers go? I remember math was simple, right? Bring over the 2x and everything else, so we get negative 2x minus y e to the xy, and then I divide. dy dx equals negative 2x minus y e to the xy over x e to the xy minus 2y. And there's your derivative. And you can use this for all sorts of different types of applications. Alright, real quickly I want to go over another natural log property one right here. So let's take a look here at number 7. Let's say we had the derivative y equals the natural log of, let's say, 2 minus e to the x over 3 plus e to the x. Now I could use my rule 1 over this times the inside quotient rule. But I remember the natural log of a over b becomes the natural log of a minus the natural log of b. I can separate it out, rewrite it. Sometimes rewriting it is kind of nice. One thing that really got me excited about mathematics when I first learned it was trigs and logarithms, because there's always so many different ways you can expand on these. And we get 3 plus e to the x. So when we take the derivative, dy dx, this becomes 1 over, the derivative natural log is 1 over 2 minus e to the x. Don't forget, multiply by the derivative of my inside, my chain rule, negative e to the x, minus 1 over 3 plus e to the x times the derivative of the inside, just e to the x. You can leave it like this, or you can write this as negative e to the x over 2 minus e to the x minus e to the x over 3 plus e to the x, if you wanted. All right, kind of a quick little application right here. Number 8, let's talk about the relative extrema. What if we want to find the relative extrema? Now this should sound familiar to us. This is our first derivative test. So let's take a look at the function y equals x e to the x. And I want to find the relative extrema. Maximums, minimums. First derivative test, so we got to take the derivative. Y prime equals the first times the derivative of the second plus the second times the derivative of the first. Well, we know we're going to set this equal to 0, and if you notice, I can factor out an e to the x. I get x plus 1. Set both equal to 0. That's our zero product property. Here we get x equals negative 1, and over here, that's not going to happen. E to the x cannot equal 0. So I'm going to do my first derivative test right here. My only critical number is negative 1, f prime, and f, do my test. And I'm going to use my function, e to the x times x plus 1. If I pick numbers, something like right here, negative 2, over here I might pick 0. If I plug negative 2 in, e to the x is positive, x plus 1 becomes negative, so that's decreasing between negative infinity to negative 1. If I plug in 0, again e to the x is positive, and 0 plus 1 is also positive, it's going up. So we have there's a relative minimum here. So let's find the point. We know x is negative 1. To get y, I plug it into here. Negative 1, e to the negative 1, or negative 1 over e. So we have a relative minimum at the point negative 1 over e, and that is again because f prime of x goes from negative to positive. What if I want to find out the points of inflection? Same equation. Well, for a point of inflection, that's our concavity test. So to get a point of inflection, use the concav, take the second derivative. Well, I already have the first derivative. It was x e to the x plus e to the x. Taking the second derivative, again, product rule here, the first times the derivative of the second plus the second times the derivative of the first, which is just 1, plus the derivative of e to the x is just e to the x. Like before, it's set equal to 0. I can factor out an e to the x, but this time I get x plus 2. Take a second and verify that if you need to. Set each of them equal to 0. That's not going to happen. You can't have e to the x equal to 0. Over here, if I try solving it, I get x equals negative 2. So there's my one critical point, or my possible point of inflection. So do my sign test, the second derivative this time. How does it affect my function? Again, I'm going to use my second derivative test. So I'm going to plug into the second derivative. Over here, I might take something like negative 3. Over here, again, 0. If I plug in negative 3, again, e to the x is always positive here. Plug in negative 3 to the second one, I get a negative. So it's concave down. 0, I get a positive, positive, it's concave up. So I have a point of inflection at x equals negative 2. So again, let's find the y value. I'm going to get, if I plug that into the original function, I'm going to get negative 2 e to the negative 2, or negative 2 over e squared. So we have a POI at the point negative 2 over e squared. And that is again because 1, the second derivative equals 0, and 2, the second derivative changes signs. Alright, so that's the end of part 1. I know it's kind of lengthy here, but we went through a lot of examples here. Just remember, e is a very easy function to work with as far as derivatives and antiderivatives as well, which we'll learn tomorrow. Later. So take a look at this, and again, if you're interested in how we get the derivative of e to the x, go on to the next video, and we'll take a look there, okay? Thank you. Bye-bye.